so I want to look at this example here. It's of course a multi-part type of question based on this reaction right here. The reaction of iodine to form iodine atoms to form iodine molecules. And it says that the rate law for this reaction is given here. Just highlight it here. And they gave you the value for K. And the first question is asking what are the proper units for K. So let me go into my full screen mode, choose a pen, ink, black. Okay, so to get the units for K, which is an answer to the A part, all I have to do is rearrange this equation here to get K is equal to the rate divided by concentration of I squared. All right. Now, in terms of the units, usually, and I think that's the case here, the rate units would be M over S, and the units for M for iodine here would be M, but it's squared, so you just put M squared here. So we have to do some cancellation here. So therefore, the units of K is equal to M to the minus 1, S to the minus 1, all right? So that basically is the answer to the first part. Now, the B part, the question is asking for the concentration of I at time 2.5 times 10 to the minus 7 seconds if the concentration of I initially is 0.40 M. So the equation we're going to use for this is 1 over the concentration of I is equal to 1 over the initial concentration of I plus KT. All right. What the question is asking for is T. All right, so we have to do some algebra here. So KT would be equal to 1 over concentration of I minus 1 over the initial concentration of I. So therefore, this implies that T would be equal to 1 over K times 1 over concentration of I minus 1 over the initial concentration of I. So T would be equal to, we have to plug some numbers in, 1 over K. The K is 7.0 times 10 to the 9. And the units would be M minus 1, S to the minus 1, times 1 over, okay, I just realized I made a mistake. Let me do an erasure here because I was solving for I when the question is asking for the solution to, I was solving for T when the question is asking for the solution for I. So let me erase this here. I'm going to start off with the same equation, but we have to use a different form of it, different rearrangement. So in this case here, going back to my pen function, we're trying to find the concentration of I. So actually, we don't even need to do that much of a rearrangement here. All I have to do is plug the numbers in. So 1 over 0.40 M plus K, which is 2.5 times 10, no, 7.0 times 10 to the 9 seconds times seconds to the, I'm sorry, M to the minus 1, second to the minus 1, multiplied by time, which is 2.5 times 10 to the 7 seconds. And we need to work this out. So I would work out this part here first. So let me get my calculator here. 7 times 10 to the 9 times 2.5 times 10 to the 7. So according to my calculation, this works out to be equal to 1.8 times 10 to the 17. Okay, wrong, because this should be minus 7. So let me do this again. 7 times 10 to the 9 times 2.5 times 10 to the minus 7, and that equals 1.8 times 10 to the 3. So this part here, 1.8 times 10 to the 3, and the units for that part would be m to the minus 1. Now the 0.4 that we have here, we have to divide 1 by that number. So 1 divided by 0.4 is equal to 2.5. 2.5, okay. So this is 2.5 m to the minus 1. Now let me do a recheck of this one here just to make sure I'm doing the right thing. 7 times 10 to the 9 multiplied by 2.5 times 10 to the minus 7. Okay, so that part is right. So basically, we're adding 1.8 times 10 to the 3 plus 2.5 plus 2.5. So according to my calculation, this works out to be equal to basically 1.8 times 10 to the 3 again. All right, so 1.8 times 10 to the 3 m to the minus 1, which means that the concentration of I would be 1 over that. So 1 over 1.8 times 10 to the minus 3 m to the minus 1. And let me do that calculation. 1 divided by 1.8 times 10 to the minus 3. Okay, so 1 divided by 1.8 times 10 to the minus 3. Oh, 10 to the 3. Why did I do that? This should be 10 to the 3. So the negative sign should not be here. So according to my calculations, this works out to be equal to 5.6 times 10 to the minus 4m. All right, so that's basically how the B part is done. Okay. Okay, let me create some space here by doing some erasure. So let me erase this part here. Now the C part is asking for the rate constant, right? And the equation for the rate constant, just to remind you, let me come out of this here and go to the slide which gives you the rate constants for all the different okay, so for the question now becomes which rate constant are we going to use? Expression. These are the rate constants expressions relating to half-lives, right? So basically we have to choose the right equation. Now, how do we know which equation to choose? Well, the question says that the rate law is this, right? Which means that it's second order because the concentration of iodine is raised to the second power, right? So that means that the rate law we're going to use is this one right here. The half-life is equal to 1 over K times the initial concentration of A. So going back to this, I'm going to write down that the half-life is equal to 1 over, let me go back to this. Half-life T half is equal to 1 over, oh gosh, 1 over K times A to the A initial. So this would be 1 over the rate constant times the initial concentration of A. So that means that the initial concentration of A would be equal to well, the initial concentration of A is given here as 0.40. So all we have to do is put the numbers in. T half is equal to 1 over K, which is given as 7.9 times 10 to the 9. Unit is n to the minus 1, second to the minus 1, times the initial concentration of A, which is 0.40 m. And we just basically work this out. So 7.9 times 10 to the 9 times 0.4, and then 1 over that. So according to my calculations, this works out to be equal to 3.2 times 10 to the minus 10. And the units here would be seconds, because this cancels with this right here. We have s to the minus 1 under the 1 right here, so therefore the final units here would be s. Okay, so that answers the C part. Now for the D part, again, let me create some space here. Okay, why is this thing not erasing? Okay, something is wrong here. Okay, let me see if I can squeeze that answer down here. Well, let me do this. Okay, something is not working out here. Sorry about this. Okay, I'm going to see if I can squeeze it in somewhere here. I'm going to see if I can do it in this section here. The question is saying, if the initial concentration of I is 0.8, how much time would it take for 75% of the atoms to react? Now, if 75% of the atoms react, that means that 25% would remain. So what we need to do is find out what is 25% of 0.8. So 0.25 multiplied by the concentration of I0, which is 0.80 m. That would be equal to 1/4 of 8.8, which would be equal to 0.20 m. All right. So this would be equal to the concentration of I at that time. So therefore, going back to this equation here, in fact, let me just put a line right here. Going back to this equation here, we can say that T, let me put this up here, is what we're trying to find. So KT is equal to 1 over the concentration of I minus 1 over the initial concentration of I, and this would be equal to 1 over 0.20 m minus 1 over the initial concentration, which is 0.80 m. And so 1 divided by 0.2 minus 1, hold on, let me do this, 0.20 minus 0.80. Okay, so the answer I got here is 3.75. And therefore T, which is what the question is asking for, would be equal to 3.75. And this would be m to the minus 1, by the way, m to the minus 1, divided by K, which is again 7.0 times 10 to the 9, m to the minus 1, s to the minus 1. And let's see what that gives. So divided by 7.9 times 10 to the 9. Okay, so according to my calculation, this works out to be equal to 4.7. 4.7 times 10 to the minus 10. Okay, so that's basically, and by the way, units here would be seconds because m to the minus 1 will cancel here and here. You have 1 over s to the minus 1, so therefore this would be the answer right here, 4.7 times 10 to the 10 seconds. Okay, so that's just another example of a typical rate law type question where in this case the reaction is a second order reaction and you're asked to find different things. Initial concentration or the concentration at a particular time or the half-life. Okay, I'm going to stop here and move on to the next topic in the next video.